Hi, my name is Tete Jacob Sirichi and welcome to my YouTube channel. Today our discussion on calculus of several variables will be on surface integration, which people also call area of a surface. You remember, we learned how to find the area of a curve. When we are asked to find the area of a curve at a point, at 2 points actually, we find the integral of the point at that. So today, before the video ends, I will introduce you to what a surface integration is. Then we'll solve some sample questions on surface integration. I will also indulge you to check part 2 of this video where there is another form to this surface integration. This will be a very interesting engagement, so please come along. So let's imagine this is our room. You remember a room is a three-dimensional object, maybe in a form of a cuboid. So let's say this is the three-dimensional side of the room. And an oil happened to pour in a part of the room. And this is the diagram for the oil. The function which we hope determine to represent the oil that pour in the room is given as z equal to g of xy. That's z is equal to a function depending on xy. And we have a function dependent on xy equal to a function g dependent on xy. This means that the part of the room where there is no oil is equal to maybe the part of room where there is oil. So I hope you get that. So we said that the surface S is the graph of the function z equal to g of xy over the region Q. And this is the region Q. Then the surface integration of where the oil poured in the room is given as the double integral of the function f of x, y, z ds, where ds represents the surface. Now remember, this is double integration, so it should be based on two variables. And luckily, z is equal to another function dependent on a variable which is xy only. So we can say this is double integration of the function f, x, y, and another function g depending on xy of dx. Now what is our ds? The ds is giving us the square root of dg over dx all square plus dg over dy all square then plus 1 dx dy. Please, there is a proof for this. Now, where do we get this dg dx and dg dy from? It is just the partial differentiation of this function here with respect to s for this. Then the partial differentiation of the same function with respect to y. I hope you get that. So we can say that our integral now will be in the form the double integration of the function f of xy, another function g of xy, then the square root of, that's in place of ds, I'm substituting that. So we have dg over dx all square plus dg over dy all square plus 1. Please, the 1 is in the square root. Then you have dx dy. Then this becomes double integration. So if the limiting point of the x and the y are given, we can easily evaluate this. Please, I will indulge you to check out my videos on how to do double integration on YouTube. This will play a very major role in our understanding of this topic. So now we'll take some sample questions and see how we can put this into practice. So let's look at our first example. They say we should evaluate the surface integral, the double integration xz over y ds, where g of xy is equal to y squared over the rectangle q equal to f of xy, where x is less or equal to 0 or greater or equal to 5 and y is less or equal to 1 and greater or equal to 4. So how do we solve this? Please remember, we said that the surface integral of the function f of x, y, and z dx, or the surface integral is given as this. And we said that ds, remember ds is equal to the square root of dg over dx all square plus dg over dy all square plus 1 dx dy. I hope you know this by now. So we can say this, the integral of f of x, y, and z dx is the same as the integral of the function f of x, y, and z, the square root of dg over dx all square plus dg over dy all square plus 1 dx dy. I hope you get that. And remember we said that g of x, y, z is equal to that, and it is equal to y squared from the equation. So we can rewrite this, and f of x, y, z is, remember, is xz over y, and z is y squared. So we can say this problem is the integral spanning the double integral of xz over y, then the square root of dg over dx all square plus dg over dy all square plus 1 dx dy. I hope you get that. And remember, z is equal to y squared. We substitute into that. So we substitute our z, which is equal to the function g depending on xy, which is y squared. So in place of z, we substitute y squared. So we have the double integral x y squared over y, the square root of dg over dx all square plus dg over dy all square plus 1 dx dy. Very necessary. So, as far as we change everything now into x and y, you see that everything now is in x and y. We can substitute the limiting point. That's for x 0 to 5 and for y 1 to 4. Remember, check out my videos on double integration. This is for the first integral, the ds is for the first integral, and then the dy is for the second. So, we can say this function, y will go into y squared 1. So, we'll have xy, the integral, the square root of dg over dx all square plus dg over dy all square plus 1 dx dy. Interesting. So now, we know that g, the function g of xy, is equal to what? Y squared. That is given here. So we perform the partial differentiation of the function with respect to x. Perform partial differentiation of the function with respect to y. And we can say our dg over dx is equal to, since there is no x component there, it will be 0. Then our dg over dy will be equal to 2y. I hope you get that. So now, since we know this, we substitute, and we know the limiting point for x and y too, we substitute. So we have the integral, the limiting point for the y first, since the dy is last year. So 1, 4, then the integral, the limiting point for the x, which is 0, 5 of xy. This is our xy. So now xy, the square root of, whilst our dg over dx is 0 and dg over dy is 2y. So we have 0 square plus 2y all square plus 1 dx dy. So when we polish this very well, we have integral spanning from 1 to 4, an integral spanning from 0 to 5 of xy, then this will be 0 square is 0, then this will give me 4y square plus 1 dx dy. I can rewrite this problem as the integral spanning from 1 to 4 and the integral spanning from 0 to 5 of x, the square root of 4y square plus 1 y dy. Y dx dy. I hope you get that. I just brought this y here. It's not anything new. Now what do? We integrate with respect to x first. The integral spanning from 1 to 4. When we integrate x, we'll get half x squared of 0.5, the square root of 4y squared plus 1, then y dy. Now, I can bring my half out if I wish, so I can say half integral spanning from 1 to 4 of x squared 0.5, the square root of 4y squared plus 1 y dy. So, I'll substitute my 5 squared minus my 0 squared. Okay, so now we substitute. So we have half the integral spanning from 1 to 4 of 5 squared minus 0 squared. This on double integration. Please check out my videos on double integrations on YouTube. The square root of 4y squared plus 1 y dy. So we have half integral spanning from 1 to 4. 5 squared, that will be 25. 0 squared is 0, so we still have 25. Then we have 4y squared plus 1 y dy. I can bring my 25 out, so I'll have 25 over 2 integral spanning from 1 to 4 of the square root of 4y squared plus 1 y dy. Now, how do I integrate this with respect to y? Look at it. If I differentiate 4y squared, I will get 8y. That means y pop up. I can use integration by substitution to do this. So first, I will rewrite this function as 25 over 2 integral spanning from 1 to 4 of 4y squared plus 1 exponent half y dy. So since I've identified I will solve this using integration by substitution, I'll just let u to be equal to my 4y squared plus 1. Then I'll find du over dy, which will be equal to 8y. This will be 0. So my du will be equal to 8y dy. I'll divide both sides by 8. Du over 8 will be equal to y dy. Also, since we are doing integration by substitution, these are the values of y. We need to get their equivalent or corresponding values of u. So when y is 4, u will be equal to 4 exponent, 4 into bracket 4 squared plus 1. So that 4 squared is 16. 16 times 4, that will be 64, plus 1, that will be 65. Then when y is 1, what will be u? U will be equal to 4 bracket 1 square plus 1. 1 square is 1, times 4 will be 4, plus 1, that will give me 5. Now I'll do my substitution now. So I'll know that my 25 over 2 is my constant there. Then in place of 1 now, I'll substitute 5. In place of 4, I'll substitute 65, sorry. 65. Then, in place of 4y squared plus 1, I'll substitute u, since u is equal to that. Exponent half. Then my y dy is du over 8. This is interesting. This 1 over 8, I can bring it out again. So I'll say this is 25 over 2 times 1 over 8. The integral spanning from 5 to 65 of u exponent half du. Now, how do I integrate this? So this will give me 25 over 16. So 25 over 16. Then I will integrate this now. How do I integrate this? I'll add 1 to the exponent, divide the function by the result. Half plus 1 will give me 3 seconds. So we have u exponent 3 over 2 all over 3 over 2, then 5 to 65. So since this is divided, we can reciprocate for it to multiply. So we get 25 over 16 times 2 over 3 of u exponent 3 over 2, spanning from 1 to 65. So 2 going to 16, 8 times. 8 times 3, that will be 24. So I have 25 over 24. U exponent 3 over 2 from 5 to 65. So now we substitute 65 minus, we substitute 5. We get 25 over 24 of 65 exponent 3 over 2 minus 5 exponent 3 over 2. We get 25 over 24. 65 exponent 3 over 2 will be 524.0468. And 3 exponent 3 over 2 will be 11.1803. This minus that, so 25 over 24. This minus this will give me 512.8665. All multiplied by our 25 over 24. We'll get our final answer to be 534.2 as our surface area. I hope you get that. I hope you get that. Please, you practice more, you become used with it. Play over the video and I know you'll get a concept. We'll solve one more example on this. So we'll solve ourselves. They say evaluate the integral s square y z ds, where s is part of the plane z is equal to 1 plus 2s plus 3y that lies above s equal to 0,3 and y equal to 0,2. So how do we do that? Remember, the integral of a surface is giving us a function dependent on 3 variables, ds. So, and we say that our ds is equal to the square root of dg over dx all square plus dg over dy all square plus 1, then dx dy. Also, remember our z is equal to that. So we can say that the integral of the function that x squared yz dx will be equal to the double integral x squared y, and what is our z? Our z is given here to be 1 plus 2x plus 3y. And our ds is the square root of dg over dx all square plus dg over dy all square plus 1 dx dy. So, remember, the function g or z is equal to a function dependent on x and y, which is equal to 1 plus 2x plus 3y. So we can perform the partial differentiation of this function with respect to x, perform the partial differentiation of the function with respect to y. We can say our dg over dx, so y will be held constant. That will be equal, this will be 0, then this will be 2. Then this is constant to be 0. Then my dg over dy is equal to, this is 0, this will be 0. Since they will be constant, then this will be 3. So what do? Now we substitute In place of dg ds, we substitute 2. Dg dy, we substitute 3. Then, remember, x span from 0 to 3, and y also span from 0 to 2. So, we'll have the integral, this for the y, the first one is for the y, from 0 to 2, the integral from 0 to 3 of this function, x squared y 1 plus 2x plus 3y, then the square root of dg over dx squared, and dg over dx is 2, so we can say 2 square plus, then dg over dy 3, so 3 square, then plus 1 dx dy. So we can say this will be 0 spanning from 0 to 2, the integral spanning from 0 to 2, and integral spanning from 0 to 3 of x squared y, that's x squared y times 1 will be x squared y. X squared y times 2x will be 2x cubed y. Then x squared y times 3y will be 3x squared y squared. Then the square root of 2 squared is 4, 3 squared is 9, plus 1 dx dy. So what do I have? I can have my integral spanning from 0 to 2, integral spanning from 0 to 3 of the function x squared y plus 2x cubed y plus 3x squared y squared. Then this is a constant. 4 plus 9 is 13 plus 1, that will be the square root of 14 dx dy. Since this is constant, I can bring it out. So I can say the square root of 14, the integral spanning from 0 to 2, integral spanning from 0 to 3 of x squared y plus 2x cubed y plus 3x squared y squared dx dy. This is very nice. So now we perform the first integral with respect to x. We substitute 0, 3. Perform the second integral with respect to y. We substitute 0, 2. So remember, when our problem involved double integration, we are performing an integral with respect to one of the functions, the other one will be kept constant. So since we are going to perform integration of this function with respect to x, the y will be held constant. So we say this is the square root of 14. The integral spanning from 0 to 2. That will be for the y. The x, since we are going to perform the integration with respect to x, this will no more be there. So we have s, we add 1 to this divided by the constant. So we have x cubed over 3y, then plus, the y will be held constant, remember that. Then plus 2s, we add 1, 4 over 4y. Then plus 3, we add 1, so s exponent 3 over 3y squared. Then now we will have dy. So on polish further, we can say this is the square root of 14, integral spanning from 0 to 2. Then this will give me 1/3 s cubed y plus 2 over 4 is half s4y, then plus this will give me s cubed y squared dy. So we said this, remember we have to bring the limiting point 0 to 3, then this 0 to 3 for the x. Now we substitute. We have the square root of 14, integral spanning from 0 to 4. Any place we see x now, we substitute the 3. Minus 1 substitute 0. Remember, 1 substitute 0, everything will be 0, so we can choose to ignore. So we have 1 over 3 cubed y plus 1 over 2, 3 exponent 4y plus 3 exponent 3y squared dy. So this is 2. So we have the square root of 40, integral spanning from 0 to 2. 3 exponent 3 is 27 times 1/3, that will be 9y. Then plus 3 exponent 4 is 81. So we have 81y over 2. Then 3 exponent 3 is 27. So we have 27y squared dy. So now we integrate this function again with respect to y. Then we substitute our 0 2. So now we integrate this with respect to y. So I have the square root of 40, integral spanning from 0. Okay, since we are going to integrate, this will not come again. So remember integration rule. It should be 9y squared over 2. We add 1 to the 1 is here already. We add 1, divide it by the result. Then plus 81y squared over 2 divided by 2 is 4. So the last one will give us 27y cubed over 3, then spanning from 0 to 2. On polish further, we'll get the square root of 14, 9 over 2y squared plus 81 over 4y squared, then plus 27 divided by 3 is 9, so 9y cubed, 0 to 2. One substitute 0 to be 0, so we just substitute the 2, 14, we have 9 over 2 square, plus 81 over 4, 2 square, plus 9, 2 cubed. So minus zeros like that, but it will still be 0. So I have the square root of 14, 9 over 2 times 4, plus 81 over 4 times 4, then plus 9 times 8. So when we simplify this further, we have the square root of 14, 2 going to 4, 2 times 9 will be 18, plus this 4 will divide that, we have 81. Then 9 times 8 is 72. We have root 14, 18 plus 81 plus 72 is 171. So we can say this is 171 root 14. Or if you like, you can change this to decimals. I hope you get that. So this is our surface integral, which is appearing at the region where s is between the interval 0, 3 and y between the interval 0, 2. We'll end it here today. Please remember to subscribe to my YouTube channel before you sign up. The more you practice, the more you know this. Until we meet again, my name is Kepsi.